Okay, so I told you we were going to go through number 5 and 6 in class, so I'm going to make a video for these. So number 5 from your packet says in 1991, researchers at the National Cancer Institute released the results of a study that investigated the effect of the weed-killing herbicide on house pets. They examined 827 dogs from homes where a herbicide was used on a regular basis, diagnosing malignant lymphoma in 473 of them. Of the 130 dogs from homes where no herbicides were used, only 19 were found to have lymphoma. So A just asks what's the standard error of the difference in the two proportions. Now, if it just asks for standard error and we're not doing a hypothesis test, we do not pool. So you only pool for hypothesis testing when you're assuming that the two proportions are equal. So here is the general formula for standard error when it's not pooled. It's basically the same thing that we've been doing, but obviously not with p hat pooled or q hat pooled. You use the p hat and q hat from your samples. So we're talking about dogs with herbicides and dogs with no herbicides. So I'm going to let H be herbicides, and I'm going to let N be no herbicides. So I know that my p hat for herbicides I'm going to do by taking 473 over 827, and that gives me 0.57. And then the p hat for no herbicide, I'm taking 19 over 130, which gives me 0.15. So to find the standard error, what I'm doing is taking the square root of 0.57 times 1 minus that, so 0.43, over my N1, so there are 827 dogs in that group, plus 0.15 times 0.85, so group 2, the herbicide group, or the no herbicide group, sorry, over 130. So I am doing the herbicides minus the no herbicides. So when I put that in my calculator, I get 0.035. So that's how you find a standard error that's not pooled. So now let's look at part B. It says construct a 95% confidence interval for this difference, and it says check your conditions. So I already have our conditions written down just because it would take me a long time. So the independence condition in both groups, one dog having lymphoma should not have an effect on another dog having lymphoma. Randomization, it's not random, but the 827 and the 130 dogs should be representative of all dogs. The 10% condition is met. Success failure, again, since it gave me the number of successes and the number of failures, or the number of successes for both groups, it's easy to find the number of failures. So I don't have to show my work here. If there are 473 dogs with lymphoma in the first group, to get the number of dogs without it, I would just take 827 minus the 473. And then for group 2, there were 19 dogs with lymphoma, and, sorry, that should say 111 dogs without. So all of these are greater than or equal to 10. And then independent groups, it's reasonable to assume that the two groups are independent of each other. So my conditions are met, so I can use the normal model to perform a 2-proportion z interval. So we're doing a confidence interval, so we have to write the z interval and not the z test. So what I need for a z interval is I need to take the proportion, the p hat, of the dogs with the herbicides minus the sample, so the p hat for the dogs without herbicides. I'm going to need that. I'm going to need my standard error of the difference, which I actually found in part A. And then I'm going to need a critical z-value. So the nice thing about the critical z-value is it's no different than our 1 proportion. So it says construct a 95% confidence interval. So that's just 1.96. The standard error we found above from part A was 0.035. And our sample difference, all we're going to do is subtract. So you're going to take the 0.57 minus the 0.15. So that gives me 0.42. So then what I'm going to do is I'm going to put this into the confidence interval. So the way a confidence interval, the actual formula, is p hat 1 minus p hat 2 plus or minus the critical z-value times the standard error of p hat 1 minus p hat 2. So obviously my group 1 is the herbicides and my group 2 is the no herbicides. So I'm taking 0.42 plus or minus 1.96 times 0.035. So when I do this, I get about when I subtract 0.351 and then when I add 0.489. So I've done all of the mechanics. So then usually I would write a conclusion, but if you notice part C, it says write an appropriate conclusion. So we're going to wait for the conclusion until the next part. So I've already written that out. There's 2 ways that you can write this. The first way is what I usually do. So I said I am 95% confident that the proportion of pets with a malignant tumor in homes where herbicides are used is between 35.1% and 48.9% higher than the proportion of pets with lymphoma in homes where no pesticides or herbicides are used. It should say herbicides. But the reason why I do this is we know that we're taking herbicides minus no herbicides. And since I'm getting a positive number, right, I know that this had to be bigger. So it had to be higher. The other way you can write it is I am 95% confident that the true difference between the proportion of pets with a malignant tumor where herbicides are used and the proportion of pets with a malignant tumor where no herbicides are used is between 35.1% and 48.9%. But the most important part is that you either say that it's a difference, or if you're putting it in this context, you say that the first one is either higher or lower than the second one. The other important thing is using this one that I made sure I talked about it in the correct order. Same with this. So since herbicides came first, I mentioned herbicides first. Same thing up here. Herbicides came first, so I mentioned it first in the sentence. Okay. All right, so that would be a confidence interval. So let's look at number 6. So number 6 says, in 1998, a San Diego reproductive clinic reported 42 live births to 157 women under the age of 38, but only 7 live births for 89 clients aged 38 and older. Is this strong evidence of a difference in the effectiveness of the clinic's methods for older women? So the first thing I'm going to do is label what I'm using. So I'm going to use U for women under 38. And I'm going to use A for women 38 and older. So the only reason why I didn't use the O for older than 38 is just because it looks like the O for the null hypothesis. So I just used A for above. So here we go. My hypotheses, right? My null would be that they're equal to each other. So the proportion of women under 38 would equal the proportion of women above 38. Now we turn this into a subtraction statement, so under minus above should equal 0. Then my alternative, notice that it says strong evidence of a difference. It doesn't say an increase or a decrease, so it would be that they're not equal to each other. So turning this into a subtraction statement, we would have not equal to 0. So then my conditions, so in both group, one woman's live birth should have no effect on another woman's live birth. It's not random, but we can assume that the 157 and 89 women are representative of all women. The 10% condition, same thing, it's less than 10% of all pregnant women. Now if I look at the success failure condition, I put a little asterisk. So it said that there were 42 live births for the first group for under the age of 38. So if there were 42 live births, that means 115 were not. The other one said 7 out of 89, so there were 7 live births and 82 not live births. Notice that this does not meet the success failure condition because there are not at least 7, or there's not at least 10 successes, there's only 7. Before you just say I can't do this problem anymore, the one thing that we can do to still be able to complete the problem is look at the pooled successes. So we know for hypothesis tests we have p-hat pooled. So what we're going to do is we're going to find that value. So the way I would do that, remember, is taking my number of successes from group 1 and the number of successes from group 2 and divide it by the total number in your sample. So the first sample had 157. The second sample had 89. So my p-hat pooled ends up being 0.199. As long as my successes are above 10 using the p-hat pooled, we can still run through the trial. So I would still take the sample size for the people above, but I would times it by the p-hat pooled. So that would be 89 times 0.199. And when I do that, I get 18. So 0.199 times 89 is about 17.7, so 18. So since this is still above 10, we still run through it, so we're okay. So then the last condition, the independence group condition, one group should be independent of the other. So because we meet the success failure condition using the pooled data, we can state my conditions are met, so I can use a normal model to perform a 2 proportion z-test. So here we go. For our z-test, right, we need our sample difference. So we did under 38 minus above 38. So that, we're going to actually find the proportion. So under 38 was 0.268. Over 38 was 0.079. So when I subtract those, I get 0.189. Then I need my p-hat pooled. We found that already above. But again, remember, it's your number of successes for both groups over the total number of samples for both groups. So we found that, and that was 0.199. Then we need our standard error for p-hat pooled. So here's where It's a little different than confidence intervals, right? We use the p-hat pooled times q-hat pooled, so that would be 1 minus the 0.199. So that's 0.801. Then it's over your first sample size. So our first sample size was 157. Then we do again the p-hat pooled times the q-hat pooled over our second sample size. So our second sample size was 89. So once we do this and take the square root, we get 0.053. So now we're ready for the normal model. So here's my normal model. The mean difference should be 0. We observed a mean difference of 0.053. Now, if we look, this is a two-tailed test because it's not equal to. So if we could observe a difference of positive 0.053, we could also observe a difference of negative 0.053. Remember, you go to the same distance from 0 on the right and the left. So I'm going to find a z-score, and I'm going to use it for the 0.053 because that's what I actually observed. So you do the observed difference minus the mean divided by the standard error. Sorry, guys. The standard error is 0.053. My observed difference is 0.189. So this will be 0.189, this will be negative 0.189. I don't have you guys in class to stop me from making my mistakes. So my z-score is 0.189 minus 0 divided by 0.053. So when I do that, I get 3.566. So now I'm doing 2 times the probability that I get a z-score that's greater than 3.566, right? Because we can do it once just for one of the tails and multiply it by 2 since they're symmetric. So I'm taking 2 times 0.0002, because when I put this into normal CDF, right, 3.566 is my lower bound, 1,000 is my upper bound. So I get this, and I multiply it by 2 because it's two-tailed. So when I do that, I get 0.0004. This is definitely a low p-value. So I'm going to write my conclusion. My p-value is low, so 0.0004. So I reject the null hypothesis. There is strong evidence to suggest that there is a difference in the effectiveness of the clinic's methods for older women. And remember, when you're having a hard time with these conclusions, just look back up at the question, right? It told me what to state. It says, is there strong evidence? And since we rejected the null, there is strong evidence to show that. So now part B. If you concluded there was a difference, estimate that difference with a confidence interval. So we already have our conditions. So I'm just going to state that my conditions are met. So I can use a normal model to perform a two-proportion Z interval. Now, remember my formula is this. I have almost everything I need, but I do not have this piece because what I found was my standard error pooled. When I do confidence intervals, I'm not assuming that they're equal, right? In fact, I actually showed that there was a difference. So I need the standard error not to be pooled. So my standard error for under, we're going to stick with the same order, under 38 and above 38. So under 38, right, my proportion was 0.268. So I take 0.268 times 0.732 divided by that sample size, so 157, plus my p hat for above 38 was 0.079 times 0.921 over 89. That was that sample size. So that value is 0.045. And then again, p hat 1 minus p hat 2, or in this case, under and above, we found that, and it was 0.189. So it doesn't tell me what confidence level to use, so I'm going to use a 95%. So I'm taking 0.8189 plus or minus 1.96 times 0.045. So when I do this, my lower bound I get 0.101. My upper bound I get 0.277. So since we're doing under minus above, this is saying that the true difference, right, is between 10% and 27.7%. So the effectiveness is higher for women under 38. So what I'm going to say for my conclusion, and I'm going to type this because it's just going to be easier, is I am 95% confident that the difference in effectiveness of the clinic's methods for women under 38 is between 10.1% and 27.7% higher than the effectiveness for women aged 38 and older. Now, the only thing is because we don't pool for this, technically, remember, we didn't meet the success-failure condition. So I am going to say, however, I am cautious when using this interval because the success-failure condition was not met for women over 38. So that is how you do a confidence interval, and there was a little reminder for hypothesis testing. If you need any help, let me know, but remember your quiz over chapter